Yeah, we left off after having talked about compression, R truncation, and then also the FTT signal processing with FTT and DWT, and also we talked about separating the noise from the high value signals using RPCA, and how all of that, if it's slaved to the master law, that the output comes with the important energetic and uncertainty certifications that we can use in downline higher level processes like learning. And so here we are, chapter 4, we're getting into learning, the regression and model selection, and with the master law. Regression is the most fundamental tool in the empirical sciences, and it's also the backbone of modern machine learning. And the basic question for learning is, given a collection of input and output pairs, maybe covariance and responses, maybe causes and effects, features and targets, whatever it is, the question is, can you find a function that maps the inputs to the outputs so that you can predict the output of a new input that you have never seen before? That's the fundamental core problem of learning. Now, in the simplest case, you just assume the function is linear, right? The output is a weighted sum of the inputs, and you want to find the best weights. This is linear regression, and this has been just the workhorse of statistics for 2 centuries. But modern data science, as we talked about before, it deals with a much more complex set of situations, namely high-dimensional inputs, nonlinear relationships, tiny sample sizes, structured prior knowledge about what the function should look like. And so within the master law framework, regression is going to always be weighted, such that the fit is measured in a metric that reflects the physical geometry W and the reliability of each measurement. So measurements that are less noisy, they get more weight. State dimensions that are more physically important also get more weight. So we're not just making some kind of cosmetic modification with these weights. It simply changes which solution is found, and it ensures that the solution is optimal in the physically meaningful sense. So the master law framework, it's also going to incorporate what we call prior knowledge through a technique that's called maximum a posteriori estimation. Of course, this is MAP or MAP. And the idea of MAP comes from Bayesian statistics. So instead of just minimizing the error between the model's predictions and the data, you also have to penalize solutions that are implausible given your prior beliefs about what the function should look like. And the prior is encoded in a matrix called Q, that's the operator prior, and Q describes which parameter values are a priori, which are more or less likely to be a priori. And the result then is just a regression that finds the best balance between number 1, fitting the data, and number 2, respecting that prior knowledge. The MAP estimate has a clean formula. It just involves inverting a matrix that combines the data information with the prior, producing both the best fit parameter vector and, crucially, a matrix called the sigma ID, which we've talked about sigma ID before. Sigma ID quantifies the uncertainty in those parameters. So the sigma ID is a identification covariance. It tells you how uncertain you are about the system, given both the data you have seen and the prior knowledge that you started off with. And the matrix propagates through every downstream step, tracking how identification uncertainty affects predictions, how it affects control, how it affects decisions. It just lives forever with the system once it's identified. There are 2 classical regularization techniques that fit naturally into this master law framework. Ridge regression, it penalizes the sum of squared parameter values, and that of course corresponds to a Gaussian prior in the MAP framework. It shrinks all the parameters towards 0, and that prevents overfitting when the number of features is large relative to the number of data points. And then there's lasso. Lasso penalizes the sum of absolute parameter values, which correspond to a Laplacian prior. And this tends to produce sparse solutions. Well, many parameters are set exactly to 0, and that effectively performs an automatic feature selection in the system. Both techniques are applied to the geometry-weighted data matrix so that the regularization respects the physical importance of different features. The appropriate regularization strength is chosen by model selection. That's comparing candidate models on held-out data using a criterion that accounts for both prediction error and for the identification uncertainty, sigma ID, and the truncation costs from earlier chapters. Now, model selection is the meta problem of deciding not just the parameters of the model, but which model to use in the first place. A model that's too simple is going to be underfit. I mean, it's going to miss important structure of the data. But a model that's too complex will overfit, meaning it's going to memorize the training data and it's going to fail to generalize, and it won't work in any kind of real situations. So the right model is somewhere in between an underfit and an overfit model. What the master law framework provides is a principled model selection criterion that combines three terms. It's going to combine the prediction error on held out data, like cross-validation loss, and then a penalty proportional to the trace of sigma ID, which grows as the model becomes more complex and less identifiable, and also a penalty proportional to the truncation cost from the reduced order representation, which is going to grow as the rank of the representation is increased. Now, this three-way balance, what does it do for us? It's going to ensure that the model selection accounts not just for statistical overfitting, but also for the identifiability of the parameters and the computational cost of the representation. So again, you can see now the sophistication and power of the master law if it's used throughout the system. So here I'm going to let you just take a look at this. Go ahead and pause the video and read anything that you'd like to read through here. This is a much more detailed depiction of how we're dealing with regression and model selection. Here's the mathematics you can look through. I'll pause down here too. You can pause the video and look at this as much as you'd like. And then, of course, we've got a little bit more down here until you get to the code sample. So you can read through that. And then we don't need to look at the code, but I'm going to just move on to the next chapter, Chapter 5. Chapter 5 is about decision trees, random forests, ensembles, these kinds of classifications with structure. Classification actually goes beyond prediction. Regression predicts a continuous number, but many of the most important problems in data science require a discrete decision. Is the email spam or is it legitimate? Is the tumor malignant or is it benign? Does the sensor reading indicate a fault or does it indicate a normal operation? These are all classification problems, and they require some different tools. Now, the most intuitive classification tool is the decision tree. A decision tree is exactly what it sounds like. It's just a flow chart of yes or no questions about the input features, and they always lead to a classification at each leaf. The leaf is, of course, the final answer. Now, each internal node of the tree asks a question like, is feature 7 greater than 3.2? It's a specific question. And then it branches left or right depending on the answer. The tree is learned from data by choosing at each node the question that most reduces the uncertainty about the correct class. So the measure of uncertainty used to build a decision tree is called impurity. The most common measure is the Gini impurity, such that at any node, if you randomly picked 2 data points and they belonged to different classes, you would make an error. The Gini impurity measures how often that would happen. So a pure node, one where all data points belong to the same class, has 0 impurity. But a maximally impure node, where every class is equally represented, has the highest possible impurity. Within the master law framework, the features used to compute impurity are first pre-weighted by the geometry matrix W. This is going to ensure that the splits chosen by the tree are based on physically meaningful variation instead of just raw numerical magnitude. Features that carry more physical information, higher weighted in W, they have proportionally more influence on the tree structure. Now, a decision tree grown to full depth will typically overfit. The standard remedy for overfitting, the standard remedy is pruning. And that's just removing branches of the tree that don't provide sufficient improvement to justify the added complexity they bring. And so the master law framework modifies the standard pruning criterion also, so that it's going to include a penalty proportional to the identification uncertainty sigma ID associated with each subtree. Subtrees that depend on poorly identified features, like features about which the data provides little information, these are penalized more heavily, and thusly they are pruned first. And this produces trees that are not just statistically parsimonious, but they're also epistemically conservative, meaning that they only make fine distinctions when the data supports them. Random forests is like a crowd of decision trees, because a single decision tree is often not very accurate, because small changes in the training data can lead to very different trees, So that's a phenomena that we call variance, and the solution for variance is just the random forest. It's an ensemble of many decision trees, and each tree is going to be trained on a random subset of the data and a random subset of the features, so that the final prediction is the majority vote for classification anyway, or the average vote for regression. Anyway, the final prediction is the majority or average across all trees in the forest. Now, random forests dramatically reduce the variance while at the same time maintaining low bias, and they're among some of the most reliable general-purpose machine learning algorithms that we have available to us. But within the master law framework, each tree in the forest uses the geometry-weighted features and the uncertainty penalized pruning criterion. And so the sensor selection methods from Chapter 3, like weighted QR, pivots, and ESOC, these can be used to guide which features are most informative and which features should be included in the random feature subsets. And then the out-of-bag, the OOB error, this is the prediction error on data points not included in each tree's training set. The OOB is computed using the geometry-weighted loss. Again, it's going to ensure that the evaluation metric reflects the physical importance. So again, if you want to read through the random forest and ensembles for classification, you can obviously do that here. I'm just going to scroll down so that we can see the math. Notation, standing primitives. You'll see a pattern as you read through this. Here's your algorithms and recipes. Randomized linear algebra. And down here you're going to get to the code samples, where we're not going to pay much attention to those right now. Instead, we're going to go to the next chapter, Chapter 6. And Chapter 6 is where we get into neural networks. And we're going to see how the master law begins to get really powerful here. Deep learning. This is universal approximation, basically, but there's still structure in the universal approximation. So really over the past 15 years or so, neural networks and their deep multi-layered successors, they have achieved powerful results, remarkable results across an amazing range of tasks. Recognizing faces in photographs, translating between languages, generating realistic text and realistic images, predicting protein structures. They can diagnose diseases from medical stands. It's just really amazing. And the common thread here is that neural networks are universal function approximators, such that given enough layers and neurons, a neural network can approximate any continuous function to arbitrary accuracy. And the training process, adjusting the network's parameters by gradient descent on a loss function, that training process can find good approximations from the data alone without requiring the user to specify the functional form in advance. Now, within the master law framework, the neural network's most natural role is just learning the lift. That's a mapping, psi, that takes the original state and transforms that into a higher dimensional space where the dynamics look linear. And this is called operator learning. It's one of the most active areas of modern applied mathematics, actually. A neural network encoder learns to map observed data to the lifted space, and then a neural network decoder maps it back. So this is autoencoders and the like. Now the dynamics in the lifted space are constrained to have the master law structure, conservative and dissipative parts, inputs and outputs. And the training process learns both the lift and the operators at the same time. So that's key. As long as the master law is present, the neural network will learn both the training and the operators. It will learn both the lift and the operator simultaneously. Standard neural network training minimizes the average prediction error across training data points, and it treats each data point equally. But within the master law framework, training is modified to use the geometry-weighted empirical risk. Each training example is weighted by the importance assigned to it by W, and examples from physically important regions of the state space contribute more to the loss, and the network learns to be more accurate there. And then the operator prior, or the matrix Q from the regression chapter, this also plays a role. Instead of pure L2 weighted regularization, the network parameters are penalized by a term that reflects prior knowledge about the structure of the operators. And this is again the MAP, the map framework. Find the network parameters that best balance data fit and structural plausibility. For parametric operator learning, this is where the network is learning a specific operator, like the flow map of the master law's discrete twin or something like that. But where there is parametric operator learning, the MAP framework gives not just a best fit set of parameters, but also gives the identification covariance, sigma ID. For a neural network, this covariance is computed using a linear approximation to the network's behavior near its operational parameters, a technique that we get from statistics of nonlinear models. Now the result, of course, is an approximate uncertainty quantification for the learned operator. And this is going to feed into the uncertainty budgets for subsequent control and subsequent decisions. And these are the later chapters. When the neural network when its learned operators are used in a control context, so think, for example, as the model in a model predictive controller, whenever these network's learned operators are used for control, they have to respect the structure of the master law. In particular, the reduced conservative matrix J sub R must be skew symmetric. That reflects the mathematical structure of the conserved flow. And the reduced dissipation matrix lambda R, it has to be positive semi-definite, which is going to reflect the physical requirement that dissipation cannot spontaneously create energy. If the neural network learns operators that violate those constraints, which it often will since it has no built-in knowledge of physics otherwise, then the framework applies a convex projection to correct them. It's going to find the nearest operators that satisfy the constraints in the least squares sense. And this projection is the mathematical expression of the principle that physics must be respected even when the model is learned from data. So we have a great advantage by embedding the master law into our deep learning processes. Go ahead and take a read through this if you'd like. We can look at the mathematics here as well. Down in number 5 again is going to be algorithmic recipes. And numerical notes. We've got diagnostics and acceptance checklists. And final operational statement down here, and some usage notes, and then of course the code we're going to skip. So obviously if you'd like to read that through that, you're welcome to do so. We're going to move forward and discuss the next chapter where we're actually getting into data-driven dynamical systems. Okay, so here's where we're going to get into Koopman, DMD, sparse identification of nonlinear dynamics, Havoc, these types of dynamical systems. Imagine that you're watching a flock of birds perform their amazing aerial murmurations. There could be thousands of birds, and they're wheeling and they're turning in perfect coordination. They're forming these kind of shapes that ripple and flow. It's almost like a living liquid or something. And you have a camera, and you can record exactly where every bird is at every moment, but you don't have any rule book. Nobody has the equations that govern how each bird decides to move. All you have is the data, the observations themselves. And the questions is, can you recover the rules from the recording, just from the recording alone? This is actually a central challenge of data-driven dynamical systems. And it's one of the deepest problems in all of the applied sciences. The laws that govern physical, biological, and engineered systems are often just unknown. They're not like the law of gravity, for example. You can't just cherry pick the governing functions just out of the system. They might be partially known, They might be known in principle, but far too complicated to work with them directly. And so what we have then, increasingly, is just the data. Just enormous quantities of measurements, time series, sensor recordings, just the data. And the question is whether we can use the data to discover the underlying rules of motion or not. What are the equations that describe how the system evolves from one moment to the next moment? Now, this is not an abstract mathematical exercise that we're talking about. The same challenges, they arise across an astonishingly wide range of real-world contexts. You'll see it in climate scientists. Their researchers want to learn reduced models of atmospheric circulation from satellite observations because the full physics are computationally intractable. In neuroscience, researchers want to learn how populations of neurons evolve through their collective states because we can record neural activity, but we can't directly read out the underlying biophysics of what's going on. Manufacturing is another place where we can see that engineers are going to want to learn how a production process drifts over time from the sensor data because the chemistry is too complex to model from the first principles. You'll see it in finance too, where analysts want to learn how market variables evolve together because the true generative process of how markets evolve is it's unknown. Now, in all of these cases, the answer has to come from the data itself. The first major technique in this chapter is called dynamic mode decomposition, or DMD. And the key insight behind DMD is both it's simple and surprisingly powerful, such that even if a system is genuinely nonlinear and if it's complicated, its short-term behavior near any particular operating condition is approximately linear. So linear systems are the ones we understand best mathematically. They obey superposition, their future states can be computed exactly, and their long-run behavior is determined just by a handful of specific patterns called modes. And so, DMD, dynamic mode decomposition, is a systematic procedure for extracting those linear patterns directly from the data. That's what we're talking about. Now here's the idea in concrete terms. So suppose you have a time series of measurements. It could be snapshots of your system taken at regular intervals. DMD is going to be looking at pairs of consecutive snapshots and asking what linear transformation applied to the first snapshot best produces the second snapshot. And it finds that transformation. It's called the transition operator. It finds it by solving a least squares problem across all the pairs simultaneously. And the result is a matrix that encodes the dominant linear dynamics of the system. Its eigenvectors are the dynamic modes, spatial patterns that evolve independently over one another. The eigenvalues are going to describe how each mode grows, decays, or oscillates over time. Now, within the master law framework then, this procedure is modified to account for geometry. The snapshots are weighted by the geometry matrix W before the least squares problem is solved. What this means is the directions in state space that are physically more important, perhaps because they carry more energy or maybe because they correspond to some observable variables. But anyway, they're going to exert more influence on the learned transition operator. So the result is a geometry-aware transition operator that's better aligned with the physics of the problem, and it's better suited to plug into the reduced master law equations. Now, there is an extended DMD as well, so that's going beyond linearity. Because pure DMD, it just assumes that the original state variables are the right ones to use. But for genuinely nonlinear systems, a better strategy is to first lift the state into a higher dimensional space, using the lift function psi from the master law, and then to apply DMD to that lifted space. And this extended version is called eDMD, or the extended dynamic mode decomposition. Okay? The idea connects directly to a beautiful piece of mathematics that's called Koopman operator theory. If you're not familiar with the Koopman operator, it's one of the most important and amazing mathematical objects that we can discover. It's an infinite dimensional linear operator that describes how every possible measurement function of the state evolves over time. Even if the state itself evolves nonlinear, certain measurement functions, these are called the Koopman eigenfunctions, these functions evolve with perfectly linear dynamics. And EDMD is essentially an attempt to find good approximations to those eigenfunctions from the data. And it does that by choosing a rich library of candidate measurements, candidate functions, and then finding the linear evolution that best fits the data in the library. So you're pre-selecting some functions, and then you're finding the data that fits those functions. And in practice, the lift psi, it must be a polynomial expansion of the state variables, or a set of radial basis functions, or the output of a neural network trained to find the best lifted coordinates. And once the lift is applied, then the geometry-weighted DMD procedure, it's going to find the reduced transition operator in that lifted space. This operator can then be projected back to the master law's Port-Hamiltonian structure. The conservative part is forced to be antisymmetric, and the dissipative part is forced to be positive semi-definite. That, of course, ensures that the learning model is physically consistent even when the data alone would not guarantee it. Now, there is a different approach to data-driven dynamical systems called SINDY. That's the sparse identification of nonlinear dynamics. Now, where DMD looks for a matrix that maps one snapshot to the next, SINDY looks for an explicit differential equation, a formula for the rate of change of each state variable in terms of the current state. The key assumption is parsimony, such that real physical laws tend to be sparse. They are going to involve a small number of terms, like Newton's second law says that force equals mass times acceleration, not the sum of hundreds of complicated nonlinear terms. And the laws of thermodynamics, the laws of fluid dynamics, the laws of electromagnetism are all expressible as relatively compact equations. Even though the behaviors that they describe can be extraordinarily complex, there's still just a limited number of terms in any equation, and that's really the assumption that we're making when we're using SINDY. And SINDY exploits this parsimony concept by setting up a large library of candidate terms, polynomials, trigonometric functions, products, ratios, and then it asks which small subset of these terms with what coefficients are going to best explain the observed rates of change in the system. So this is a sparse regressive problem, and it's solved using techniques like lasso, which were discussed in Chapter 4. And the result is an explicit interpretable equation, the actual symbolic mathematics, that the data has identified as the governing law. Now, within the master law framework, the SINDY regression is done with geometry weighting, exactly as in the regression chapters. The candidate terms are weighted by W, the prior over coefficients is set by Q, and the identification covariance, sigma ID, quantifies how uncertain we are about each term in the discovered equation. Then, once the equation is discovered, its linearization around any operating point is computed and is projected to the Port-Hamiltonian structure, and that again ensures that the learned model fits seamlessly into the master law's architecture for later control and reduction. Then one of the most important practical decisions in data-driven dynamical systems is just choosing how many modes or basis functions to keep. The rank of the reduced model. Keep too few and the model is going to be inaccurate, but keep too many and it's going to be computationally expensive, statistically unreliable, and potentially it'll be unstable when it's used for control. The master law framework, it provides a principled answer to this problem of rank selection. The total cost of a rank R model has three parts. Firstly is the approximation error. That's the signal in the discarded modes that the model is ignoring. Second, you have the truncation noise cost. And this process noise that flows through the discarded directions and accumulates into additional uncertainty, and that's going to be captured by the trace of the truncation operator applied to the noise covariance. And then thirdly, there's a statistical penalty. The complexity cost of the model is related to the identification covariance sigma ID. Now the optimal rank balances all three of these. So it's going to be large enough that the approximation error and the truncation noise are acceptable, but it's going to be small enough that the model is statistically reliable and computationally tractable. So this is a genuinely novel contribution of the master law framework, because classical model order selection criteria like AIC or BIC, these penalize the model complexity to prevent overfitting, but they don't account for the physical noise that enters through the truncated models. And by explicitly including the truncation noise costs, the master law gives a much more physically meaningful criterion for model selection.